Hello guys. In fact, in the previous sessions, we have presented mainly the main features of the control systems. We have presented the main parts, the controller, the plant, the sensor, showing the physical or the software characteristics of each part. We have also presented the main components or the main frames coming from with the control systems, mainly the Laplace and the inverse Laplace transform, the Taylor development in order to get a linearized system if the system is nonlinear. Also, we have presented how to represent a system or how to present a system either in time domain, starting by the modeling in the and calculating the characteristic equation of a system, or using the state space representation, or in frequency domain by presenting the transfer function. We have also presented mainly the features of each of these representations. Then we have focused on the time domain analysis. The first point is to have a closed loop system before going through the time domain analysis, and the second point is to have a stable system, of course, as if the system is not stable, it's not important anymore to study the time domain response. So for the time domain, we have presented first the first order systems and the second order systems with the overdamped, underdamped, and critically damped systems. We have calculated the features of the system either in graphically or analytically. And we have presented the errors, how to calculate an error for a system of type 0, type 1, or type 2, for a step, for a ramp, or for an impulse input. So this session will mainly focus on the stability of a system to see if the system is stable or not, and if it's not stable, how to stabilize it. So the outline of this presentation is as follows. We first will present an introduction of the stability. Second, we'll go into through the first and the easiest stability method, which is the placement of poles. Here we calculate the closed loop poles, and based on these poles, we can directly define if the system is stable or not. Whenever the closed loop poles are difficult to calculate, we can go through the Rousse-Hurwitz algorithm in order to see if a system is stable or not. Of course, each of these methods have some features, some advantages, some limitations. We will go through them later on in this presentation. And we will finish this session by some case studies that will be shown later on. So first, let's see this flow chart. When talking about stability, we have two options: the open loop and the closed loop systems. So for the closed loop systems that we will be discussing in this presentation, we'll present the placement of poles and the Rousse criterion. As for the open loop systems, we have mainly three different methods. There are more than these methods, but mainly we have these three different methods. The body plot. From the body plot, we will calculate the phase margin and the gain margin. That will determine if the system is stable or not. The Nyquist plot, and we have also here the Nyquist stability criterion. And last, we have the Rousse-Locus plot that will be discussed in the next session, in fact, in the next lecture. Mainly the open loop methods are also used for the control, and also this will be emphasized later on in this course. So in this lecture, we'll be focusing mainly on the closed loop methods. These two methods, as I have presented before, that are the placement of poles and the Rousse-Hurwitz criterion. For the placement of poles, we have we have to determine first the closed loop poles, and based on these closed loop poles we have to look at the values, at the real values of these poles. If all are have negative real parts, the system is stable, otherwise the system will be unstable. But the main problem with this method is the complexity of the system, because as you may know, systems may be of order 5, 6, 7, or even higher. So the difficulty is to compute the roots of the system. As for roots criterion, in fact, it will determine if the system is stable or not, but will not help us to stabilize an unstable system, because it just tells if the system is stable or not. It doesn't give any extra clue to help in order to stabilize a system. But it has one main advantage. It is if we have a parameter within the system, for example the gain, which is variable, it has a value of k. Using the closed criterion, we can determine the range of values of this parameter k in order to keep the system stable. So we will start by the first method. So as presented in the previous chapter, in the time domain analysis chapter, all the closed loop poles must have a negative real part in order to have a stable system. The first step is to compute the closed loop tensor function of the whole system, as we have presented earlier. And the second step is to determine the poles of the function, of course, of the closed loop function. At this level, one can also plot the real versus the imaginary axis. In fact, we have two methods to show if the system is stable or not. The graphical way, when plotting, when inserting the poles in the xy graph, the real versus imaginary graph, and we can here see if we have at least one of the poles with a positive real part, the system will be unstable. And the second method is an analytical method. We will focus only on the poles and effectively on the real parts of the poles, and to make sure that all have a negative value. So consider, for example, the system. It is a closed loop system where we have only a plant which tensor function is 3 over s plus 1 into s plus 2. And step response. So we calculate first the closed loop pole, the closed loop tensor function, and based on the closed loop tensor function we can determine that we have the three different poles, two complex conjugate poles 1 and 2, and a real pole which is of order minus 2.672. So the two complex conjugate poles have a negative real part with which value is minus 0.164. So the three poles have negative values, thus the system is stable. 29, 31, 26, 8, and 0. And we use the function roots in order to get the poles of this, or the roots of this function. We can also use a third method, which you know very well, which is the TF to ZP function, and we'll get in this case the poles, the zeros, and the gain of the closed loop tensor function. So as shown, we have at least two poles with positive real parts, so the system will be on. And also this is visualized in this session also, in this slide also, and you can see these poles. Note that when we have a pole and a zero which are superposed, these values will not appear when you'll be doing your hand calculations, because you will do the simplifications. But as we have discussed previously in class, MATLAB will not do any simplifications, thus they will appear, but in your calculations you will simplify them. So after placement of poles, we'll go to the Roos algorithm.